value a function approaches when its input x approaches some other value. Limits can be evaluated as right-hand, left-hand, or general limits which approach from both sides. Left-hand limits approach from the left, and right-hand limits approach from the right. For a limit to exist, the left and right-hand limits must match with each other. A general limit may not exist, but its left and right-hand limits may exist. Therefore, limits may not exist where there are asymptotes, such as the function 1 over x at x equals 0, or where there are too many oscillations, such as the function sine of 1 over x at x equals 0, or where there are jump discontinuities, where the limits from either side don't match. When evaluating a limit, basic algebraic properties like the limit, sum, and difference rule apply. When evaluating a limit, first try direct substitution. If that doesn't work, as in you end up with an intermediate form, try algebraically manipulating your function, like factoring and canceling. After that, retry direct substitution. Once you end up with a number, drop the mic. If the algebra doesn't work, use L'Hopital's rule. When discussing the end behavior of a function, we can take the limit of the function as it tends to positive or negative infinity, and if it converges, then we have found its horizontal asymptote. When evaluating an infinite limit, focus only on the highest power terms, since higher degree terms are more important in terms of end behavior. There are many applications of limits like derivatives and integrals, and thus intermediate value theorem, which states that for a function f of x that is continuous on the closed interval ab, and f of a is not equal to f of b, then f of x takes on every value between f of a and f of b on that interval. A function is continuous at a point x equals a if the limit as x approaches a of f of x exists, f of a exists, and the limit as x approaches a of f of x is equal to f of a. A function is continuous if it is continuous at every point on its domain. The derivative of a function is a measure of how sensitive it is to change, a measure of how much it will change in the next instant. They are tiny changes in a function, and are a measure of the instantaneous rate of change. Recall the slope formula y2 minus y1 divided by x2 minus x1. We will rewrite this as f of x plus h minus f of x divided by x plus h minus x, which simplifies to f of x plus h minus f of x divided by h. To find the instantaneous rate of change, we will shrink the length of our interval h down to 0. We can do this by using limits, rewriting this as the limit as h approaches 0. We now have the definition of a derivative, and to evaluate it at a point, we will just substitute the x value of our point into the derivative formula. When evaluating this limit, there will always be some sort of algebraic manipulation needed, as by default the limit evaluates to 0 over 0. Instantaneous rate of change can also be defined as the slope of the tangent line along the curve of the function. Therefore, to find the tangent line at a point, find the derivative at the point. This will give you the m, or slope, of the tangent line. The normal line is the tangent line, whose slope is the negative reciprocal of the tangent lines. Therefore, it is perpendicular to the tangent line. A function is differentiable only if it is continuous. Differentiability implies continuity, but continuity does not imply differentiability. A function is differentiable if it is continuous at each point and the slopes from both sides of a point match. This means a function that has points where sharp cusps, corners, or discontinuities occur is not differentiable at these points. When writing a derivative function, it is denoted as f prime of x. When writing the derivative operator, it is written as d over dx, though it is properly said as d dx. There are easier ways to find derivatives than using the limit notation. For a constant function, the derivative is 0. For a function f of x is equal to k of x, where k is a constant, the derivative is just k. For a function f of x is equals to x to the n, where n is some constant, its derivative is x to the n minus 1. Derivatives have algebraically intuitive sum and difference rules, but their product and quotient rules aren't so intuitive. To prove the product rule for derivatives, we're going to assume that a function h of x is equal to f of x times g of x. Using the limit definition for the derivative of h of x is equal to the limit as delta x approaches 0 of h of x plus delta x minus h of x divided by delta x. We can expand it to f of x plus delta x times g of x plus delta x minus f of x times g of x all divided by delta x. Now, we can go ahead and use some subtraction and addition methods as well as some factoring to manipulate this limit, and then we end up with h prime of x equals f prime of x times g of x plus f of x times g prime of x. Of a sum or difference of functions are the sum or difference of the derivative of those functions. These are the sum and difference rules for derivatives. For a function h of x is equal to f of x divided by g of x, the derivative of h of x is g of x times the derivative of f of x minus f of x times the derivative of g of x, and all of that divided by g of x squared. An easy way to remember this is low d high, min high d low over the square of what's below, where d means the derivative of the function. Low is the function in the denominator, and high is the function in the numerator. This is called the quotient rule. Transcendental functions have their own unique derivatives. For example, the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, the derivative of an exponential is the original function times the natural log of its base. This means e to the x is its own derivative. The derivative of log base a of x is 1 divided by x times the natural log of a. This means the derivative of ln x is just 1 over x. For a composite function f of g of x, its derivative is f prime of g of x times g prime of x. This is called the chain rule. And it says that when taking the derivative of a composite function, take the derivative of the outer function and multiply by the derivative of the inner function. An extension of the chain rule is implicit differentiation. For an implicit equation, to find the derivative dy dx, differentiate both sides with respect to x, and when dealing with another variable y, differentiate it using normal differentiation rules, and then multiply by dy dx, the derivative of y with respect to x. An extension of both the chain rule and implicit differentiation is finding the derivatives of inverse functions. Differentiating the equation f of f inverse x is equal to x, and solving for the derivative of the inverse, we find that the derivative of the inverse is 1 over f prime of the inverse function. It is possible to take the derivative of a derivative, or in what is called a second derivative of a function. In a lot of cases, you can have more than two derivatives. A derivative taken with respect to x to the variable y is written as dy dx. Some other notable derivatives include the derivative of secant x, which is secant x times tangent x, the derivative of cosecant, which is negative cosecant times cotangent, and the derivative of cotangent, which is negative cosecant squared. Each inverse trigonometric function has their own derivatives. There are many functions out there with their own unique derivatives. Derivatives in context are typically used to express rates of change. In physics, the derivative of position, the rate at which position changes with respect to time, is velocity. Speed is the absolute value of velocity. The derivative of velocity, and therefore the second derivative of position, is acceleration. The derivative of kinetic energy with respect to velocity is momentum. The time derivative of momentum is force. In economics, marginal cost is the derivative of the cost function, and it estimates the cost to produce an additional item at the margin. Marginal revenue is the derivative of the revenue function. Profit is the revenue function minus the cost function, and marginal profit is the derivative of the profit function. The maximum profit can occur where the marginal cost and marginal revenue equal each other. Another examples of derivative in context are related rates, which involve finding a rate of something given known quantities of things related to that rate, hence the name related rates. Some examples include the rate at which the radius of a circle changes, given the rate at which the area changes, the area of that circle more specifically. We could also be given the radius itself. Another example of related rates is the rate at which the volume of the sphere changes, given the radius and the rate at which the radius changes. There are lots of other examples of related rates. An application of the derivative is using it to find tangent lines to approximate values close to the tangent line of the original function. This is called linear approximation, and in general, it's written as f of x is approximately equal to f of a plus f prime of a times x minus a, where a is some input point along the function. Another application of the derivative is L'Hopital's rule, which states that if evaluating a limit yields an intermediate form, write the limit as a fraction and take the derivative of the numerator and denominator, and then try direct substitution again. The mean value theorem states that if a function f is continuous on the closed interval ab and differentiable on the open interval ab, then there must be some point c such that f prime of c is equal to f of b minus f of a over b minus a. A function has maximums at points where the y value is higher than most other points. A function has minimums at points where the y value is lower than most other points. We call these maxes and mins extrema. At the extrema of a function, the derivative is 0. So to solve for the extrema of a function, we find where the first derivative of the function is 0 or undefined. The points where this occurs are called critical points. If the first derivative is positive, the function is increasing. If f prime of x is negative, then f of x is decreasing. Thus, to determine what type of extrema is at a critical point, look for the sign changes of f prime of x. If f prime of x changes from positive to negative, it's a max. If f prime of x changes from negative to positive, it's a min. To find global extrema, find the critical points and substitute them into f of x to see which points give the highest or lowest value. The extreme value theorem states that if a function is continuous on a closed interval ab, then the function must have a maximum and minimum value on the interval. The second derivative of a function is positive, f of x is concave up. If it's negative, f of x is concave down. A point of inflection occurs when f double prime of x changes signs, or where the concavity changes. If f prime of a is 0 and f double prime of a is positive, there's a relative minimum at x equals a. If f double prime of a is negative and f prime of a is 0, then there's a relative max at x equals a. Optimization is the process of making something fit a certain set of constraints in the best way possible. In calculus, this means finding mins and maxes in context. An example could be finding the optimal dimensions for a fence given a certain amount of material. The original function and its first and second derivatives all have unique relationships with each other. Keep in mind, there's more than a second derivative. There can be a third, fourth, or even fifth. It just depends on the function. To find the net change of a function, we would add the tiny changes in the function over time. This could also be thought of as summing points of the derivative function over time to find the net change in a function. This process is called integration and is the inverse operation of differentiation. There are many ways to approximate the area under a curve, whether it be by drawing rectangles like LRAM, RRAM, or MRAM, or by drawing trapezoids like TRAM. If we were to take lots of infinitely small rectangles with a width dx and a height f of x and sum them, we could perfectly approximate the area under a function. Recall that we are essentially adding small changes in the function or adding points components of its derivative to find the net change. Therefore, the area under the curve is just the net change of the antiderivative of the function. This means that to find the area under the curve from a to b, we must first find the antiderivative of the function and then find the difference in the antiderivative from a to b. This is the first fundamental theorem of calculus, and it is written as the integral from a to b of lowercase f of x times dx is equal to its antiderivative capital F of b minus capital F of a, which is equal to the area under the curve of lowercase f of x from a to b. Because integrating involves finding the antiderivative, the derivative of an integral for a function f of t dt with bounds a to x is just f of x. This is the second fundamental theorem of calculus. An integral with bounds such as a and b is called a definite integral and will always yield a number. An integral with no bounds is called an indefinite integral and yields the antiderivative of the function. To find the antiderivative of the function, we reverse the rules of differentiation. When we have found the antiderivative, we add the constant of integration c to account for the possibility of a lost constant when we differentiate a function. The integral of some constant k is kx plus c. The integral of x to the n is x to the n plus 1 divided by n plus 1 plus c. Transcendental functions have their own unique integrals. Integrals have sum and difference rules that work just like the differentiation sum and difference rules. When we integrate a composite function, we use u sub to rearrange the integrand to something that can be integrated. There are no integral quotient or product rules, so we have to use lots of various integral techniques depending on the integrand, like integration by parts. There's also integration using trigonometric substitution, integration using partial fraction decomposition, and much more. Given a function h of x is equal to f of x times g of x, we know h prime of x, or the derivative of f times g, is fg prime plus f prime g. Integrating both sides, fg is equal to the integral of fg prime dx plus the integral of f prime g dx. Keep in mind when we integrated the derivative of fg, the integral and the derivative cancelled out. Solving for the integral of fg prime dx, we end up with the integral of fg prime dx is fg minus the integral of f prime g dx. We now have ourselves what in some cases can be considered as an integral product rule. This is called integration by parts, and is based on reversing the differentiation product rule. For this to work, you need to have a function that you can choose to differentiate and one that you can integrate. You must also be able to integrate the function that you differentiated and the function that you integrated. Some useful techniques when doing integration by parts are the DI tabular method and the LIAP method. Keep in mind that there are a lot more integration techniques than just this. A differential equation is an equation that relates one or more unknown functions and their derivatives. There are many ways to solve differential equations, the easiest being to integrate both sides of the equation if it is possible to do so. Differential equations represent rates. Something that is directly proportional is in the form of y equals kx. Something that is indirectly proportional is in the form of y equals k divided by x. Solutions for differential equations can be verified by substituting in the derivatives of y, you could call it also f of x, into the differential equation. If the derivatives satisfy the differential equation, y is a solution to the differential equation. One way to solve differential equations is by sketching slope fields. A slope field is a picture of the solution set to a differential equation that helps determine if there is a general antiderivative. To sketch a slope field, we set the derivative y prime in terms of a function f of x comma y, and we then make a table for x, y, and y prime, and find values for y prime along a set of points. We then sketch a small line segment with the slope of y prime at the respective point. After sketching line segments for all points, we look for a general curve pattern and see if we can sketch an antiderivative out of the slope field. Another way of solving differential equations is using separation of variables. First, separate the y and x variables to opposite sides of the equation. This includes dy and dx. Then integrate both sides, keeping the plus c on the x side. Then solve for y. For cases where a particular solution is given, solve for c and then solve for y. When the rate of change is proportional to a certain amount, we could write this as dy dt is equal to ky, which models exponential growth. Solving for y, we end up with y is equal to c e to the kt, where c is the constant of integration. Logistic growth is modeled by the differential equation dy dt is equal to ky times the quantity a minus y, and has the general solution y is equal to a divided by the quantity 1 plus b times e to the negative A times K times T. K and A are constants. Logistic growth starts as exponential growth and plateaus at y equals A. We call A the carrying capacity or limiting capacity. As y approaches A, dy dt approaches 0. As t approaches infinity, y tends to A. Y of t has a point of inflection when y is equal to A divided by 2, and this is where dy dt is at a maximum. Logistic growth is very useful, particularly in biology for modeling population numbers. One way to approximate solutions to differential equations is Euler's method, which is using a series of tangent lines to model the curve of the solution to the differential equation to approximate the solution of an initial value problem. The integral, like the derivative, has many applications. The average value of a function from a to b is 1 over b minus a times the integral from a to b of f of x dx. In physics, the integral of acceleration is velocity. The integral of velocity is position. To find displacement from a to b, integrate the velocity function from a to b. To find the distance traveled, integrate the absolute value of velocity. The position at t equals b is the integral of the velocity function from a to b plus the position at t equals a. To find the area between two curves from a to b, assuming f of x is the top curve and g of x is the bottom curve, take the definite integral from a to b of f of x minus g of x for functions in terms of y. If there are two functions g of y whose curve is to the right of f of y, the area between them is the definite integral from c to d. Keep in mind these bounds are in terms of y. And the definite integral is of g of y minus f of y. If we assume the area bounded by a function is the base of a solid, to find the volume of the solid, we can integrate cross sections inside the curve, or rather the base of the solid, to find its volume. If we were to rotate the bounded region around the x-axis, we would have a solid of revolution, whose volume could be found by integrating tiny cylinders across the shape. This is called the disk method, and its formula is pi times the integral from a to b of the function squared times d. If rotated about the y-axis, the integrand and integral need to be in terms of y. When a gap is formed from the revolution, we use the washer method, which is the same as the disk method, but in the integrand, we subtract the gap formed by the revolution in the integrand. The arc length of a function denoted L is equal to the integral from a to b of the square root of 1 plus y prime squared times dx. In physics, the integral of force with respect to displacement is work, and the integral of force with respect to time is impulse. Calculus is elegant and easy.